So picture this. You're standing in line, waiting for your morning coffee. The barista is steaming milk. The line is just totally stalled out. So naturally, you pull out your phone.
Oh, yeah, the classic instincts.
Yeah,
We've all been there.
right. You open an app, swipe your thumb down the screen, and release. And in less time than it takes you to blink, I mean, under 200 milliseconds, this perfectly curated, chronologically sorted list of global thoughts just appears. Breaking news, maybe a meme or two, right in the palm of your hand.
And we just expect it. Like, we actually get annoyed if it takes half a second.
Exactly. We
Yeah.
demand that it happens instantly, but we are completely blind to um, the sheer violence of the data processing happening underneath that simple swipe.
It really is an illusion.
Mm.
An illusion of instant, effortless connection, mainly because the user interface is just so clean and simple.
And that is exactly why we're going into the absolute architectural deep end today. We're looking at a really brilliant, comprehensive breakdown called Twitter System Design Production Grade Architecture, written by Dilip Kumar.
Yeah, it's an incredible source, just wildly detailed.
It really is. Okay, let's unpack this. Our mission for this deep dive is to explore the staggering engineering magic required to serve 500 million daily active users. We are talking about balancing insane global speeds with a frankly incomprehensible amount of data.
The scale is just punishing. I mean, the source lays out these baseline numbers, and on an average, totally boring Tuesday, this system handles roughly 58,000 tweet creations every single second.
Wait, so by the time I finish this sentence, like 200,000 new pieces of text and video have just been hurled at their servers.
Basically, yeah. And that's just the baseline. During major global events, like the final minutes of the World Cup or a sudden breaking news crisis, that number spikes up to 290,000 writes per second.
That is just, it's hard to even wrap your head around.
Right, but creating the data is actually the small part of the problem. This architecture is massively read-dominant because for every one person shouting into the void, there are like 5 people listening.
Ah, so the read to write ratio is skewed?
Exactly. It's a 5-to-1 ratio. The system handles over 300,000 timeline read requests every single second.
Wow. Because for you listening, understanding this architecture is kind of like learning the secrets of a modern digital metropolis. You look at a city's skyline and it looks static and calm.
But underneath, there's just chaos.
Right. Massive subways, high voltage power grids, high pressure water mains keeping millions of people alive. To understand how this digital city handles 58,000 new thoughts a second without instantly burning to the ground, we really have to start at the front door.
Yeah, you have to look at how a tweet actually survives entering the building.
So what does that front door look like?
That front door is what the architecture calls the API Edge Gateway. And in this specific design, it's built on a massive cluster of Envoy proxies.
Okay, so it acts like a bouncer.
Precisely. It's the ultimate bouncer. Before your tweet even gets to the internal network, Envoy terminates the secure connection from your phone. Then it verifies your OAuth 2 security tokens to mathematically prove you are who you say you are.
And I imagine it handles rate limiting there, too.
So extreme rate limiting. If a malicious botnet tries to flood the system, the gateway just silently drops the traffic before it ever even touches a database.
But reading through the breakdown, there is a massive language barrier right at that front door. The source points out that all the internal microservices, the actual brains of the operation, they communicate 100% via something called gRPC.
Right, which is a hyper-efficient compressed binary protocol.
Yeah. Now, I know native mobile apps on your phone can speak that gRPC language, but if I'm sitting at my laptop, my web browser uses standard JSON, and JSON is basically bulky, plain text data, like every single word has tags around it.
It's very bloated, yeah.
So my question is, if gRPC is so much faster and better for this kind of scale, why not just force it end-to-end for everything? Like, why not just ban JSON entirely?
Well, it sounds like the obvious solution, right? But it comes down to the physical limitations of web browsers themselves. Under the hood, gRPC relies on raw HTTP2 framed TCP streams.
Okay, and browsers can't do that.
Exactly. Standard client-side JavaScript running in a web browser simply does not have the native APIs to open and manage those raw binary streams directly. The browsers literally cannot do it.
Man.
So they have to use standard REST API requests, which means they have to send that bulky JSON plain text.
So we are stuck with millions of laptops sending incredibly bloated text files. How does the system not slow to an absolute crawl trying to read all of that?
What's fascinating here is how the Envoy gateway solves this so seamlessly. It uses what's called a gRPC JSON transcoder.
Oh, so it translates it on the fly?
Exactly. When you tweet from a web browser, Envoy catches that bulky JSON request right at the edge.
Hmm.
It doesn't let it inside. Instead, it instantly translates it into a tightly packed binary gRPC protobuf message.
Wow.
And then it forwards that tiny binary package to the internal network. Once inside the perimeter, every single microservice only speaks this ultra-fast binary language.
So it's not just a translator, it's really a compressor. It's like taking a sprawling, word-heavy legal document, that's our JSON, and having a lawyer instantly compress it into a tightly packed, bulleted list of just the essential facts before handing it to the judge.
That's a perfect analogy. The judge, which is our internal network, only has to read the bullet points.
Which keeps everything incredibly fast. So, the gateway translated the message, but translating it is totally useless if we can't save it fast enough. The tweet has to go to the engine room.
Right, the storage stack. And this is where the engineering gets absolutely ruthless. The primary database chosen here is ScyllaDB, acting as the master append-only storage.
I have to stop you there, actually, because I noticed they explicitly rejected a very famous database called Apache Cassandra. And Cassandra is like the industry standard for huge data. Netflix uses it, Apple uses it. Why on earth would they rip out a proven giant like Cassandra?
It comes down to a lethal combination of two things: the latency budget and JVM garbage collection.
Okay, JVM.
Yeah, Cassandra runs on Java. And the Java Virtual Machine, or JVM, occasionally has to pause the entire application to clean up its memory. It's a process known as garbage collection.
Wait, it literally stops everything, just freezes.
Yes, they're called stop-the-world pauses.
Oh, wow.
Now, for a normal app, a 100 millisecond pause is totally invisible. But at 58,000 writes a second, a 100 millisecond pause means nearly 6,000 tweets just piled up at the door waiting to get in.
Oh, I see. It creates massive cascading latency spikes.
Right, which eventually just crashes the servers.
Yeah.
So ScyllaDB, on the other hand, is written in C++A. It doesn't use a virtual machine, and it utilizes what is called a shared nothing thread per core architecture.
Shared nothing thread per core. Okay, that sounds like a buzzword bingo winner.
Yeah.
Are you basically saying each processor core gets its own isolated memory so they don't have to wait in line to talk to each other?
That is exactly the mechanism, yeah. By giving every CPU core its own dedicated slice of memory and its own network queue, ScyllaDB completely bypasses the Linux kernel context switching.
So the cores never lock each other out.
Never. This eliminates those unpredictable pauses and mathematically guarantees that writes happen in under 30 milliseconds at the 99th percentile.
Unbelievable. So the tweet is safely on the hard drive. But alongside ScyllaDB, the source highlights Apache Kafka, which acts as the distributed event log. It's the messaging backbone that tells the rest of the architecture, hey, a new tweet exists.
Exactly, it's the messenger.
And here is where I see a massive hazard in the design. The naive way to build this is to have the API service write the tweet to the database and then turn around and send a message to Kafka saying, I just saved a tweet, go tell the timeline service.
Ah, yes. The dreaded dual write problem. It is the absolute bane of distributed systems.
Because it's basically like writing a physical letter, dropping it in a mailbox, and then pulling out your phone to call the post office to tell them you mailed it.
Right.
If your phone battery dies exactly after you drop the letter, the post office never gets to the call and your letter just sits there forever. In server terms, if a machine crashes exactly between writing to the database and messaging Kafka, the system falls completely out of sync. You have ghost data.
It's a total nightmare.
So how does this architecture prevent dropped messages or data corruption when servers are, crashing all the time?
They completely eliminate the dual write using an architectural pattern called Change Data Capture, or CDC.
Okay, how does that work?
The system simply doesn't trust the API to make two phone calls. Instead, the tweet API only does one thing. It writes the tweet to ScyllaDB, period. It gets that sub-30 millisecond success signal, and it terminates the request. The API walks away.
It just drops the letter in the box and trusts the universe.
Exactly. Because a totally separate asynchronous system, a Debezium CDC agent, is tailing the database's commit log.
Oh, so it's watching the raw files.
Yes. This agent sits there watching the raw underlying database files on the hard drive.
Right.
The absolute microsecond a new row is permanently written to the disk by ScyllaDB, the CDC agent reads that change log and guarantees delivery of the event to Kafka.
Oh, wow. So there are no race conditions at all.
None. Because the event is generated directly from the database's own undeniable truth. If the data is on the disk, the message gets sent. If it's not, it doesn't.
That is incredibly elegant. Storing the tweet safely is completely decoupled from telling the rest of the system about it. But that brings us to the central conflict of this entire deep dive.
A fan-out problem.
Right. The tweet is safely on a hard drive. But how does it get from that hard drive to the timeline of every single person following the author in under 200 milliseconds? Here's where it gets really interesting.
This is the ultimate architectural dilemma. The source outlines two traditional extremes for feed generation and explains in really great detail why both of them are technically impossible at this scale.
Let's hear the extremes. What's the first option?
The first is the pure read-on-demand model. This is how almost every small to medium app works. When you open the app, the database looks at the list of people you follow. It goes into the giant global table of all tweets. It runs a SQL query to find their recent posts, joins that data together, sorts it by time, and sends it to you.
But at this scale, doing those SQL joins across billions of rows for 300,000 read requests a second, I mean, the hardware would melt.
Oh, completely. The source notes that doing it this way takes over 2,000 milliseconds.
2 full seconds. In app time, 2 seconds means your user has already closed the app and is staring out a window. It's an eternity.
Right. Just a totally unacceptable user experience. So we absolutely cannot build the feed on the fly when the user asks for it.
So what is the other extreme?
The pure write-on-publish model, which is also called naive fan-out.
Okay, naive fan-out.
Right. So instead of doing the work when you read, it does the work when I write. When I publish a tweet, the system immediately pushes a copy of that tweet into a pre-computed timeline feed for every single person who follows me.
And those feeds are stored in a ridiculously fast memory cache, right? Like Redis.
Exactly. So when my followers open the app, their feed is already fully built and waiting for them. 0 database joins required.
But here's where this whole model hits a brick wall. Pushing data works flawlessly if I'm tweeting to my 300 followers. The system does 300 quick memory writes to Redis in the background. Easy.
Right. It's basically instant.
But what happens during the Super Bowl when a global superstar with 100 million followers drops a tweet with a video attached?
You experience catastrophic write amplification.
Which is a polite way of saying the servers catch fire.
Basically, yes.
Because if the system tries to instantly push that single tweet into 100 million individual Redis feeds at the exact same time, it exhausts the memory, maxes out the network bandwidth, and crashes the background workers. It's not delivering mail anymore. That's trying to individually hand a printed flyer to every single person in an entire country at the exact same millisecond.
And this is exactly why the architecture has to be so intelligent, because neither extreme works globally. The system has to smartly classify users in real time to decide how to deliver their tweets.
Okay, so it dynamically switches strategies.
Exactly. This introduces the hybrid push-pull fan-out router, and it hinges entirely on a magic number.
50,000.
50,000 followers.
Yes. The system literally treats authors differently based on that specific threshold. For regular users, anyone with fewer than 50,000 followers, the system uses the push model.
So background workers fetch your followers from the social graph service and just aggressively pipe your tweet directly into the Redis home timeline of each follower. Right. Because it's fast, it's pre-computed, and the fan-out is small enough that the servers can easily handle it.
Which is an amazing piece of tech, even if it comes with the existential dread of realizing you are mathematically categorized by an algorithm as just a regular user.
True. It's a little humbling.
But what happens to the superstars?
For celebrities, anyone with 50,000 or more followers, the system flips to the pull model. It completely skips the follower push.
Oh, it doesn't push their tweets at all.
Not to the followers, no. It writes the tweet only to the celebrity's personal timeline cache. Then it broadcasts a very lightweight signal, a server-sent event alert, just saying, hey, this celebrity just tweeted.
Wow. If we connect this to the bigger picture, the sheer amount of energy, electricity, and hardware this saves is mind-boggling.
Oh, it's massive.
You aren't doing 100 million pointless database writes just because a pop star posted a smiley face emoji. You do one right and just alert everyone to come look at it. And speaking of brutal efficiency, what I found fascinating in the source was this concept of activity pruning.
Ah, yes. The dormant account problem.
Right. Even for regular users in the push model, if the system notices that one of your followers hasn't opened the app in 14 days, it just stops.
It skips them entirely.
It stops pushing your tweets into their pre-computed feed. It's the architecture actively saying, you aren't paying attention, so I'm not wasting my expensive CPU cycles on you.
It's ruthless. but necessary.
Right.
If you connect this to the bigger picture, it protects the active infrastructure from being bogged down by the dead weight of dormant accounts.
Okay, so the routing is brilliant. We have regular tweets being aggressively pushed into our pre-computed Redis feeds and celebrity tweets sitting in their own separate, isolated buckets.
Right.
But when you, the listener, actually swipe down on your screen, you don't see two different buckets. You see one seamless, perfectly blended feed. How does the app stitch those pushed regular tweets and those pulled celebrity tweets together so perfectly without taking seconds to load?
That magic happens in the timeline fetch engine, utilizing a technique called an in-memory min-heap k-way merge sort.
Okay, min-heap k-way merge sort. Let's break that down because it sounds like a graduate-level computer science exam. How does that actually zipper these feeds together?
Well, when you open the app, the engine grabs your pre-computed regular feed from Redis. Then, it simultaneously pulls the recent tweets from the specific celebrities you follow.
Okay, so now it has a bunch of different lists.
Exactly.
Oh.
But instead of dumping all of this into a giant list and trying to sort it from scratch, which takes way too much processing power, it uses the k-way merge. Because each individual feed is already sorted by time, the algorithm just looks at the top tweet of each pile, grabs the newest one, puts it in your feed, and then looks at the tops of the piles again.
It's like having 50 distinct decks of cards that are already sorted. You don't shuffle them all together and sort them again. You just look at the top card of every deck, pull the highest one, and repeat. You never have to read the whole deck.
Exactly. By only comparing the heads of the lists, the algorithm merges these massive data streams in constant or logarithmic time, producing a single, perfectly chronological JSON feed in under 5 milliseconds.
That is just so smart. It handles the sorting beautifully. But there's another fascinating problem the source brings up when you start actually scrolling through that newly sorted feed. The pagination problem. Or, as I like to think of it, the offset bug.
A classic database issue, yeah.
Yeah.
Traditional databases use limits and offsets for pagination. They say, give me items 20 through 40.
Right, which works great for a static list. But in a real-time feed with 58,000 writes a second, using offsets is like telling someone to bookmark page 20 in a novel, but a ghost is constantly pasting new pages into the front of the book.
Exactly. Everything shifts downward.
Yeah, if I'm looking at tweet number 20 and 5 new tweets arrive at the top of my feed while I'm reading, my old number 20 is now technically number 25. So if I scroll down and the app asks the database for the next 20, it's going to give me duplicate tweets I've already read.
It creates a terrible, glitchy user experience. And at a database level, it requires scanning and discarding thousands of rows just to find your new place, which destroys performance.
So how do they fix it?
To solve this, the architecture completely abandons offsets. Instead, it uses seek cursor pagination, anchored by 64-bit Snowflake IDs.
I love the name Snowflake ID. What makes a Snowflake ID so special that it fixes the shifting page problem?
A Snowflake ID isn't just a random number. It actually embeds an exact epoch timestamp directly into the ID integer itself. It means the ID is mathematically guaranteed to be strictly monotonically increasing.
Meaning a larger ID number guarantees the tweet was created more recently.
Precisely. So instead of asking the database for item 20, which changes, the app asks for tweets strictly older than ID 1952439.
Oh, that is genius, because even if 500 new tweets just dropped at the top of the feed, it doesn't matter. You are asking for a specific moment in time. The baseline never shifts.
Exactly. You never see a duplicate no matter how fast the timeline is moving above you. It turns a heavy, unpredictable database scan into an instantaneous lookup.
It's a perfect example of using data structure design to solve a user interface problem.
Absolutely.
Now, speaking of those new tweets arriving at the top of the feed, we all know that little floating pill that pops up at the top of the screen saying, arrow up, 2 new tweets.
The update badge.
Right. The source details how that signal gets to your phone, and it uses server sent events, or SSE. I have to admit, I was genuinely surprised by this.
Really? Why is that?
Well, whenever you read about real-time data on the web, chat apps, live sports scores, everyone always screams WebSockets. WebSockets are the famous standard. Why did they explicitly reject WebSockets and choose SSE instead?
It's a very deliberate architectural choice based on extreme resource constraints. WebSockets are bidirectional. They keep a heavy, persistent two-way channel open so data can flow back and forth constantly.
Okay, but a timeline update badge is strictly unidirectional, right? It's just the server notifying the client that new stuff exists.
Exactly. The client doesn't need to talk back. You don't need to send data to the server to make the pill pop up.
Right.
And because you don't need to talk back, the memory difference is staggering. Keeping an idle WebSocket connection open, with all its heartbeat pings and TCP overhead, consumes about 50 kilobytes of RAM per user on the server.
Okay.
An SSE connection, which runs on standard HTTP multiplexing, consumes only about 4 kilobytes of RAM.
Wow. Less than a tenth of the memory. And consider the math on that. If you have 10 million people staring at the app at the same time, saving 46 kilobytes per connection is gigabytes of expensive server RAM saved instantly.
Because it's so lightweight, a single gateway node can handle over 500,000 concurrently open SSE streams. It's exactly the right tool for a massive one-way signaling requirement. WebSockets would have bankrupted the memory budget for literally no added benefit.
So what does this all mean? Next time you're standing in that coffee shop line and you casually swipe down on your screen, think about the sheer orchestration happening in the palm of your hand.
It really is a marvel of modern distributed systems.
Your single swipe gets translated from JSON to binary gRPC on the fly. It bypasses Java garbage collection pauses by using C++ shared nothing cores. It triggers asynchronous change data captures to avoid dual write failures. It navigates a hybrid fan-out model that treats your friends and global pop stars completely differently.
It's an unbelievable symphony of technology.
Right. It executes a K-way min-heap merge sort in memory and uses time-stamped snowflake IDs to make sure you never see the same post twice. All of this happening across thousands of servers globally just to deliver you a tiny hit of dopamine in under 200 milliseconds.
This raises an important question, though, because as we synthesize all this engineering, we saw how the system physically cannot survive unless it mathematically segregates society into two distinct classes: regular users and celebrities.
Right, it's hard-coded into the architecture with that 50,000 follower threshold.
Which leaves you with a really heavy thought to chew on. As we interact online, is the architecture of our software simply reflecting our real-world social hierarchies, celebrities up high, the rest of us down here, or is it actively enforcing those hierarchies because it is literally the only mathematical way the servers won't catch fire?
Does the code mirror us, or do we conform to the code so it doesn't break? It's a fascinating blurred line between computer science and sociology.
It really is.
That is definitely something to think about the next time you're waiting for your barista to hand you that latte. And maybe give them a second to catch up. After all, they don't have a K-way merge sort running in their head. Thanks for taking this deep dive with us.